Okay, this is section 6.5, trig form of a complex number. And let's just get started right now with example 1. Translate from standard form to trig form, z is equal to 3 minus 2i. So the first thing I want to do is I want to plot my complex number. And just as a quick reminder of how to graph a complex number, make my axes. What used to be the x-axis, or our horizontal axis, is going to be our real number axis. And the y-axis, or the vertical axis, is now our imaginary. Okay, so if I have 3 minus 2i, that means I'm going to go over 3 to the right and 2 down, and that's actually right about here. So I'm going to connect those. That means along my real axis I went 3, and on my imaginary I went negative 2. So it looks very similar to our triangles that we've been working with all semester long. And so in order to find the trig form, we're going to need to do a couple of things. We need to find our r, which is the magnitude of our z, of that vector, and we need to find that angle right there. So we're going to do a couple of things. And these are not things that are that's new to you. This is just a different way to look at it. So the first thing I'm going to do is I am going to find my r. And so this is that r right there. And that's going to be using our Pythagorean theorem of 3 squared plus negative 2 squared. And that gives me the square root of 13. Alright, so I now know my r. Now I have to find my theta. And my theta is going to be my b over a. So the tangent of my angle is equal to the negative 2 over 3. So theta equals arctan, or tan to the minus 1, of negative 2 over 3. And that's not on our unit circle, so we are going to have to use our calculators. And I get that theta is about negative 33.6901 degrees. And that's okay because to have this value, because it is not on our unit circle. And it is the correct angle for where I'm at. I'm in that fourth quadrant. And so I can use negative 33. Or I could do the coterminal, which would be about 327, but we'll just stick with this one. And now to write this in trig form, it's r times the cosine of theta plus I sine of theta. If I distribute the r, I forgot to write the r there, hold on. And I just have to place my r and my theta. So the square root of 13 cosine of the negative 33.6901 degrees plus the square root of 13 sine the negative 33.6901 degrees I. Now if you notice here, the theta is the same in both, so this is the same as over here, and these both have that square root of 13. So there's a bit of a shortcut we can write. And it's just r, so the square root of 13, cis, so that stands for cosine I sine of our angle. Alright? So you could write it out either way. You could write it out the way we have in longhand with the 13 cosine theta plus r sine I theta. Or you could do CIS. Either one is acceptable. Alright, let's move on to example 2. Okay, so example 2 is very similar to example 1. I'd like you to pause your video right now, and I want you to graph where z is. Okay, your graph should have look like mine. So, first thing we need to do is we need to find r. So pause your video and find r, and check your answer with me. And you should have got that r is equal to 4. Now find your theta. Now I'm going to do this theta with you because it's a little different than the last one. And I know that the tan of theta equals 2 root 3 over negative 2. And if I simplify that, I get tan of theta is equal to the square root of 3. And looking at my graph, I know that I need to be in that third quadrant, and the square root of 3 is on our unit circle. So that tells me that my theta is going to be 4 pi over 3. Now the reason I don't want to use the reference angle here is I want to make sure I have my plus and minuses in the right spot. So I'm actually looking at theta starting from my horizontal axis all the way over. Okay? And now we just have to write it out. And I'm going to use the shortcut. 4 CIS 4 pi over 3. And that's it. That's example 2. Let's move on to example 3. So example 3 says translate from trig form to standard form. So basically I've given you the trig form. I want you to figure out what it originally was. What's the standard form? What's your a plus bi? And so the first thing I'm going to do is I'm going to spread out my CIS. So I have 3 root 2 cosine of pi over 6 plus I sine of pi over 6. Now if I find the cosine of pi over 6 and the sine of pi over 6, I'm just going to fill those in. Cosine of pi over 6 is root 3 over 2. Sine of pi over 6 is 1/2. Now, just distribute the r. So take 3 root 2 times r root 3 over 2. And that's going to give me 3 times the square root of 6 over 2 plus, now do the same over here. And that's going to give me 3, and I'm going to put the I between the 3 and the root 2 so I don't lose it. 3i root 2 all over 2. And that's it for translating it back from trig form to standard form. So that's pretty fast. So I'd like you to do example 4 on your own. Example 4 says we're going to translate z equal to 7 CIS 5 pi over 3 to standard form. Okay. Pause your video and work out the problem and see if you match me. Okay, if you expanded it out and then simplified, you should have ended up with what I got. Negative 7 root 2 over 2 minus 7i root 2 over 2. Okay, so now we're going to move on to the last two examples in this section. Make sure you read over the little bit of notes there so that you understand what's going to be going on. We're going to be looking at operations of working with our complex numbers in our trig form. So let's start with example 5. Okay, so we're going to be multiplying two trig forms together and dividing them in example 5. So let's start with the multiplying. In the multiplying, what I'm going to do is I'm going to multiply my two r's together And then I'm going to add my 2 thetas. And then I do the same for my sine. And your shortcut will work for this as well. And what I use to help me remember what I need to do is it's kind of similar to working with exponents. I multiply my coefficients out in front, but I would add my exponents. And it kind of follows those same rules. So filling in my blanks. R1 is the 9. R2 is 4. Cosine of theta 1 is 2 pi over 3 plus 17 pi over 3. Or excuse me, 17 pi over 6. I looked at that wrong. And it's the same for the sine. Okay, so all we have to do is multiply the 2 out in front. So 9 times 4 is 36. And now we have to add our two thetas together. So get a common denominator. Common denominator would be 6, so I'm going to multiply the first one by 2, and I get 4 pi over 6 plus 17 pi over 6. Okay, and now let's just reduce, or combine and reduce. So it gives me 36 cosine of 17 pi plus 4 pi is 21 pi over 6. Well, those both reduce by 3, so that gives me 7 pi over 2 plus the I sine of 7 pi over 2. And write it as my shortcut. Okay. Alright, so you could write it out like we did. Do you think we probably could have done our shortcut to begin with and just add our thetas and multiplied our r's? Yeah, but I wanted to show you how it all works together the first time. So now let's divide. So because we are doing division, we are going to divide our r's. But this time what we're going to do is we are going to subtract, and I'm going to use the shortcut this time, my first theta over my second theta. And it's really important you pay attention to which one you use. Whatever is on top of your original fraction, so in this case, Z1 is on top, then R1 needs to be on top, and you're going to start off with theta 1, the first theta. Okay, so really pay attention to get things in the right order. So R1 is 9 over 4 CIS. Theta 1 is 2 pi over 3 minus 17 pi over 6. And now I just simplify. Well, the 2 pi over 3 becomes 4 pi over 6 minus 17 pi over 6 gives me 9 pi over 4 CIS of negative 13 pi over 6. And that's example 5. Okay. Let's move on to the last example where we are going to apply De Moivre's theorem. Please make sure you look over the theorem so you have an idea of what we're going to be doing. And another way this is it's powers of complex numbers. We're going to be looking at powers. Okay? Okay, so using de Moivre's theorem to calculate -1 plus I root 3 to the 28th power, we would not want to have to multiply this out 28 times. That would take a lot to do. So it's always great to have little shortcuts, and that's what de Moivre did. He proved a way of being able to multiply out complex numbers. And first thing we have to do is we have to get it into trig form. So let's get this into trig form. So if you remember to find trig form, we need to find r, and we need to find theta. So let's find r first. R would be -1 squared plus root 3 squared. And that's the square root of 1 plus 3, which is going to come out to be square root of 4, which is just 2. Now for theta, I kind of need to know where I'm located. So I'm going to do a quick sketch of this to help me figure out, because I need to make sure I get the right angle. And I have a -1 as my real number and a positive root 3. So that means I'm up this way. So that's -1, and that's root 3. So for my tangent, it's -root 3 over 1, or -root 3. Well, if it's in the second quadrant, tangent's -root 3 at 2 pi over 3. So there's my theta. So if I put this now in trig form, so the first thing we need to do is put it in trig form, and z is going to equal 4 CIS of 2 pi over 3. But I want z to the 28th. Did I say 4? I'm sorry. That's supposed to be 2. I wrote 2. But I want z to the 28th power. So the way I'm going to do that is I'm going to take my r to the 28th and my theta. And again, thinking back like we did with the last two problems, remember I said relate back to exponents. When I multiplied two things together, I added the exponents. When I divided things with the same basis, I subtracted. When I take an exponent to an exponent, I multiply them. So I'm going to take that 2 pi over 3 times 28. And just simplify this. Now you're probably thinking, whoa, wait a second, 2 to the 28th, that's huge! And it is. So just leave it 2 to the 28th. Okay? CIS, 2 pi over 3 times 28 is 56 pi over 3. And we're done. Alright, so these were the notes for 6.5 on trig form of a complex number and and powers of a complex number. I'm sorry about that. If you have any questions, make sure you come to class.